Hi, we're Team 13, and we're making a PCB oven for ELEC 291. Now, we were tasked with making a PCB oven because for the rest of the year we're going to use an EFM8 board, and we're going to cook it ourselves. We are given a DE10 light, which we could configure to a CV8052 microcontroller. We are also given an LCD display, speaker, and keyboard, a temperature sensor, and an oven unit with a solid-state relay, basically VCC and ground power control. Now to go over the requirements. We need to do the programming in the assembly language. Additionally, we need to use the processor that is not the N76E003, which we used in a previous lab. Instead, we're going to use the DE10 light. We need the oven to go over 5 determined states with initial parameters through connecting a solid-state relay. For this, we used a finite state machine to loop through each state and determine whether to move to the next. Now, a PCB oven isn't as simple as it seems. This isn't just a microwave, but a device with multiple cooking states that is augmented to cook your PCB board perfectly. Firstly, the oven has to hit a temperature of 150 Celsius at 100% power. It then goes to a rest state where it stays at 20% power for 60 to 120 seconds. After this, it does another burst of power until it's at 220 to 230 Celsius. It then goes at 20% power again for 30 to 45 seconds. Lastly, it then turns off and waits until it's cooled to at least 60 Celsius before finishing and restarting to the first state. We need to input these initial parameters, like the temperature and times, at each state. So we used the keyboard and the 7-segment hex display on the DE10 to show what is being written during the starting state. We also need to display all our initial parameters, current time, and total time, so we used the LCD display. We added a button so you could press it and change between the displays to see all the information at any time. For displaying temperature, we reused the 7-segment hex display when not in the starting state. Additionally, we also need a start-stop button, sound feedback through a speaker, an emergency exit in case of temperature reading malfunction, a way to sense the temperature through the thermal wire, a way to see what state you're in through the LEDs, and a way for the computer to read the values coming through the serial port so we could graph them over time. Now, we also added a few extra features. One of our team members was very musically inclined, so he decided to add 2 songs that play when the oven is done. This was done by reusing one of our interrupt timers so that when a song is playing, we were able to change the tone throughout each note and play the entire song. On top of the song feature, we also added 2 new additional modes you could access through a button press. The first mode configures the keyboard into a magic music keyboard by using the infrastructure created by the song feature. Any button makes a different sound which you can use to play any song. The second mode changes the oven into a microwave, where each button on the keypad acts as a predetermined cooking preset. This is like the popcorn button on your microwave at home. For the serial port readings, we added 2 graphs on top of each other, which read the temperature over time. The top one shows a closer-up perspective to how the temperature is fluctuating, whereas the bottom one shows the overall path the temperature took. In the bottom one, we also added a prediction in how the graph should look based on the initial conditions. All of this is sent to a Discord bot, which uploads the data and the graph to a Discord server, which we could all access. These are the overall results. This is how the final product worked and how it looked. Making the EFM8 board was quite tough, but we were able to do it and put it in the oven to start cooking it. As you can see, the LCD and temperature display worked, as well as the temperature plot. but unfortunately, our first board burnt. We determined that it was in there for way too long, as the oven didn't heat up as fast as we thought it would. So, we lowered the initial parameters to lower than what our lab said we should, and it cooked a lot better. Looking back at the project now, we had a lot of problems. At the beginning, we had a lot of problems with the hardware part and the serial port reading and the temperature reading not working. And all of these were very time consuming. But we were able to solve all of them. No real glitches or errors reached the end of production. But with how time consuming the initial problems were, it was a lot harder to get it finished by the due date. Overall, it was a very good first project, where we learned a lot about how hardware and software communicate. It was fun putting into perspective all the labs we've done, like the LCD lab, alarm lab, and the temperature lab, and making something from each of them. For our next project, we're going to work a lot earlier, so we could lighten the burden on our daily work. Lastly, here are some stats on our final full project.